Okay, let's have a look at the conservation of power, complex power. So first we look at the series circuit. In a series circuit, we will have many components in series, so they will carry the same current, but they might have different voltage drop. So the total voltage here will be the sum of all those voltages on the component, but we only have one current through it to all the load. So we can multiply this conjugated current onto each of the component and get this total power as a sum of individual complex power. For parallel circuit, we have the same voltage applied to the component, but each component might carry a different current. So this is the total current, which is the sum of all the current on each branch. And remember that we need to do the conjugated version of the current. And we can do this on each of the component, and therefore we have complex power on each component. So the two sum look the same. In summary, the total complex power is the sum of the complex power in individual components or elements. In practice, most of our loads are connected in parallel, which is this case, and the total complex power is the sum of complex power on each component is called the conservation of complex power. We can also prove that there is a conservation for active power. Total P is the sum of P in each component, and there's a conservation for Q, reactive power. Total Q will be the sum of Q on each component. And now we move on to another concept. Let's call power triangle through an example. In this example, they have already given us the voltage and the current. So to calculate the complex power, we only need to multiply this voltage phasor and the current phasor conjugated, and that will give you this value, 1000 at the magnitude and 36.8 at the phase angle. The real value will be 800 and imaginary will be 600. Okay, and therefore P is 800 and Q is 600. Remember, they are real value. And the apparent power, we see the magnitude of voltage multiplied by the current, magnitude of current will be 1000 volt ampere. So you can see 3 units for 3 different power. And now we can build the power triangle by putting a P part on the real axis, okay, and the Q part on the imaginary axis. And remember, P plus JQ will be S, so this will be your S, the value of S. This is called power triangle because all sides of the triangle we have just power. Okay, in this example we can see that this current phasor is lagging this voltage phasor by 36.8 degrees, and therefore we have a lagging power factor or a load, or the load is an inductive. Let's move on the next topic. This is important. How do we specify power in a load? We need to understand what is given. Okay. So far we see that we have 6 quantities related to a load: voltage, current, power factor, apparent power, real power, and reactive power. Okay. However, they are related. So to specify one load, we only need 3 out of those 6 quantities. So first case, if we are given voltage phasor and a current phasor, that is equivalent to giving voltage value, RMS voltage, RMS current, and power factor. So that's 3. Another way is to give us the voltage, the power factor, and the power. So this is normally a load. So our job is to calculate the remaining 3 parameters. So for current will be calculated by this first expression, power divided by voltage power factor. And then we calculate Q after we find I, current. We now can calculate VI and sine of theta. Now we are given power factor, which is cosine. So from cosine we can easily calculate sine, and therefore this is the next step. And finally we form S. S is P plus JQ by definition. The third way to define or to specify a load is to give you the voltage, the power factor, and the apparent power. So how do we calculate the remaining 3? First step is to calculate the current. Okay, apparent power divided by voltage will give us current, and then we can calculate Q from S and the power factor. And the final way to specify a load is to give us voltage, real power, and reactive power. So by definition, from P and Q we can calculate the apparent power S. Okay, and from S and P we can calculate the power factor. One note: whenever you answer a question for a power factor, you also need to tell if it is lagging or leading.